Okay. I originally had a huge number of slides, and I've reduced them quite a bit, and hopefully we'll get through them. And I've actually kept all the slides around, so if there's time, we might go back to some of the ones I cut out. But for now, we'll start the presentation. Now, the first thing I want to say is that I've actually rearranged things a bit. The original title said that I would talk about time travel debugging, and that's going to be at the very end. I figure it's more useful to talk about what we've done in Dyalog'. So the presentation is organized into three parts. First, we'll talk about what we're doing for nonlinear random number distributions and what strategies people have used and what we're moving to for version 19.0. Secondly, we'll talk about testing issues because, as Morton pointed out, we had some embarrassments with version 18, and our goal is to make sure those embarrassments are either rare or never ever happen again. And finally, I'll talk a little bit about my history to bring people up to date about what I've been doing over the years. So to start with, what's the reason we actually could need to use linear distributions? This all started in the days of the Manhattan Project, when Stanislaw Ulam was working on some physics problems having to do with neutrons and chain reactions. All those things involve probabilistic interactions, and they're very hard to calculate. So he came up with the notion of, why don't we just instead make a set of statistical models with random events happening, and we'll actually run the random event models and sample the probability space to figure out how things actually work. And it turned out it did exactly what he needed for his physics calculations. And a lot of other people have figured out they're useful for not just physical situations, but for financial management and projections, and also management problems. Things like, will we ship this on time? How late are we likely to be? Now, in the process of doing this sort of thing, our first problem is that the distributions like the beta distribution are nonlinear and non-uniform. Within APL, we already have a mechanism for doing uniform distributions known as question mark. Now, there's the old version, which gives you discrete values like question mark 6, to throw 2 dice. And then there's question mark 0, which gives you a number between 0 and 1 with a uniform distribution. And you can do some things with that. For beta, one of the things you can do is, in some of the subcases for its parameters, you can map those values directly from a uniform distribution to the exact sort of pattern we find for those parameters in the beta distribution. For instance, the 5-1 parameter set gives you an exponential growth distribution, and the 1-5 parameters gives you an exponential decay distribution. And wonder of wonders, a beta parameters of 1 space 1 is just the uniform distribution. However, the other parameters that you could give it give you wildly different kinds of distributions. So people have dealt with this by using a technique called inverse transform sampling. And I had code to show that, but I'll put that off because you can look that up. It's a well-known technique. The other thing people do is they use our connection mechanism to call into R from APL and get results back. Essentially, the APL interpreter is calling the R interpreter and asking it to do a calculation and give it back the results. Now, for version 19, we're going to change this. There are a number of reasons for doing it, but mostly it's to make it easier to get to a wide variety of distributions and to reduce the overhead of doing it. So for the beta distribution, the pattern is going to be the parameter, say set 2,5, and then a particular I-beam. It's 16808 I-beam. And we may change this to a system function later, but for now it's an I-beam. And then the right argument consists of 2 things: the name of the distribution you want and the shape of what you want the result to be. And more generally, the left argument is going to be parameters for the distribution. The right argument is going to be the name of the distribution and the shape you want to have for the result. And as time goes on, we'll add more and more distribution types. I have in plans to add the Dirichlet distribution because it's a variation of the beta distribution. And there's arguments for having the gamma distribution, the normal, and perhaps the log normal. And we're open to suggestions for which are the most valuable and useful random number distributions to add. Now, the things we get out of this is this mechanism takes much less space and time than, say, the inverse transform mechanism. And it has a lot less overhead than starting up and communicating with the R interpreter. And it's a native implementation written in C and C++. We use the very same algorithms that are used by R and all of the other major systems that provide random number distributions. And it's a clean framework for supporting additional distributions as we find them appropriate to add. The second theme that I want to talk about is what we're doing to deal with quality assurance for APL. Version 18 was a bit of an embarrassment, and we take that as a hard lesson, and we're working on fixing that problem. That involves several things. One is simply quantifying how much of our code, how many lines of our code are covered by our unit tests, and how many are not. And that gives us a set of problems. For the ones that are not covered, we have to write focused unit tests. And when I do these things, I want to make them useful not only as tests, but also as documentation. Because it turns out if you have written documentation as text, it suffers from the problem of becoming disconnected from the actual code. It'll start out being very good, but over time, as the code changes, the documentation suffers what you might call bit rot, and it no longer tracks what the implementation really does. If we write unit tests correctly, not only do they help us catch bugs and prevent them, but they force us to update the documentation, because if a test breaks because we change the way code actually worked, we have two choices. Either there's a mistake in the way we did it with code, we have to fix the code, or there's a mistake in the test because it no longer describes accurately what it is the code is supposed to do. The final thing, which is a softer sort of thing in a way, is we actually have to do a lot of work to look at the code that we're writing. It means a lot more review, and when we actually have a failure that our unit tests uncover, a fair bit of time in the debugger figuring out what's going on, why it failed, and how we should fix it. Now, here's an example of how I think we should write unit tests. They should be readable with well-chosen identifiers and reasonable comments, but the comments aren't the primary thing. It's the actual code that matters. This is the first part of a unit test for the integral index function. And what it says is we have an environment we set up, which is this trap, so that if we get an unexpected signal, we can react to it rather than having the whole test just blow up. And I put in some comments about what invariants are we testing. And then the pattern is I start off by creating the data we're going to work with, the left and right arguments A and B, and then we actually do the test. That is, the important thing is this line here, R becomes A iota underbar B, and then we have a function that will verify the results and either give an indication that things passed or that they failed. And if it passes, we just return by branching to 0. And if we drop down to this next line, that meant we got a result, but it was wrong. In that case, what we do is we record a note about what was happening, that we had an incorrect result. We record the expression we executed, and then the value of the result and the values of the left argument and the right argument. And of course, if we have a truly unexpected behavior, we had a domain error, a rank error, or something else, we record that fact and what the error was, and likewise, similar information. The only real difference is we don't record a value for a result because we didn't get one. Now, one of the things that's important about doing proper unit tests is you want to test not just for the happy cases where people gave you correct arguments and you got good results, but you want to test for cases where things should fail, and you want to make sure they fail in the correct way. And here is a case where we're doing an iota underbar, and it turns out our left argument, A, is a scalar. Well, that should give a rank error. And we've trapped that by setting up a trap saying, if we get a rank error, we should branch to the label rank error. So if you look at the code, it sets up the parameters for the test. Then it makes the call to A iota underbar B. And if that actually gives us a result, that's a problem, because that should have failed. So in that case, we put out a note saying, you should have given a rank error. And likewise, we say what it is we did. R becomes A iota bar underbar B, and then we return the result, the left argument, and the right argument. And now, on the other hand, if we actually did a rank error, got a rank error, we get to this label and we've passed. And there's also the possibility that we've got an error, but not the one we expected. And we want to know that too. So that's the basic strategy I want to use for unit tests. I want them to be readable. I want them to be good documentation. And I want them to be a living set of code that goes right along with the code that actually runs in the daily use of the interpreter. Now, let me turn to what I've done over the years. For the first few years of my career, I was focused very tightly on APL. I discovered APL 360 in 1969, and at that point, I was talking with some acquaintances about starting some computer science courses in the high schools of Hampton, Virginia. And so between 1970 and 73, I taught those classes and had a number of really bright students. The fellow here, a few years ago, sent me a note that he had just retired from his job as the chief technical officer of the CIA. And the other guys and people in the class, ladies and gentlemen, have also done extremely well over the years. And from there, I had kept in touch with a lot of the APL implementers. And I ended up working for a number of companies writing APL implementations and also doing applications like the 666 box mailbox that STSC used. Larry Breed had done the first implementation, and I did version 2. And while I was at STSC, I spent a lot of time working with Phil Abrams and Larry Breed and Bob Smith, who are still active in the APL community. And going on from that, I went to do some work for Burroughs. Unfortunately, I haven't been able to find a picture of Jim Ryan, but I worked with him for a number of years. And then we also did a thing called the APL machine for Analogic. And that was a moderately successful machine. NSA bought quite a few of them. And along the way, I worked with several other people like Michael Berry and Richard Suter, and met a few interesting people like Alan Kay. So that was an interesting time. Now, in 1986, I took a different turn. Having done a lot of APL, I decided I should do things with microcomputers. Alan Kay, with his Dynabook, had pointed out this was the wave of the future. So I decided I had to be part of it. So I joined Microsoft. And I did a number of things there. The first thing I worked on was Windows, and then OS2, and then Windows NT. And then I spent some time on Visual Basic and Encarta, and did some research projects for Microsoft Research, one of which was time travel debugging. We'll talk about that near the end. And mostly this is just to show a number of the interesting people I worked with. There's obviously Bill and Paul. And the fellow on the left here is Charles Simoni. He was the final interview I had at Microsoft, and essentially the person who thought I might be a reasonable fit for Microsoft. And so that worked out pretty well. While I was at Microsoft, I had a side project, which was an aviation business at Tacoma Narrows Airport. It's called Zephyr Aviation, and if you're interested, I can tell you about it. It was an adventure. And finally, in those early days, after I had been at Microsoft for a while, I left in 2007 to do an internet startup. Essentially, we were doing internet television. Our website was called Podly TV. We found all the videos continuously on the internet, and we organized them into 8,000 channels. The channels were organized by subject matter. That is, we had a separate channel for every musical artist in the world, for every sports team in the world, and we had a channel for every news organization in the world. And we also had lots of special interests like programming, photography, wood carving, needlepoint, you name it, we had it. And then after doing that, I came back to the Seattle area and did some work for Amazon between 2013 and 2015. The group I was working in there was called the Unified Subs Ledger. It recorded all the financial transactions that went through the Amazon website in a durable fashion. We were responsible for satisfying the accountants whenever they had some concerns about things in the general ledger. We could give them all the details. Now, one of the common factors in this sort of thing is Amazon, as you know, grows fairly fast. And I don't think it's too much of a secret to say that every year the number of transactions we handled went up by 2.5 times. So we had to worry a lot about scaling. In fact, we had to worry about the things that you couldn't cure by simply adding more machines to the cloud. We had to worry about what were the bottlenecks in our fundamental algorithms. We also did what I call test-driven development. The basic idea is if you have something that's beyond the quick and dirty experiments that you actually want people to use, you take the pattern of you write your test set first, all your unit tests first, and then you write your code, and you keep changing your code until the tests pass. And then as you go along, you inevitably discover that you have to change your code. Sometimes it happens because you didn't actually figure out the right way to do it originally. And sometimes it happens because the requirements change. And so that meant you had to change either the code or the tests or maybe both. And the other thing that was important is we did what we call continuous refactoring. So you discover something that you got to fix. Maybe it's a bug, or maybe it's a high demand customer. You may have to do that under pressure as a hack, but you never ever want to have hacks piled upon hacks, because at some point your code will be not understandable and subject to lots of bugs. So we had a practice of always putting in the schedule work to actually redo the code so it actually looked like we knew what we were doing in the first place instead of just stumbling along. And that actually worked extremely well. But in some ways, it's a hard discipline to follow. But we did. We had some extremely good engineers there who forced that discipline on everybody. These are some of the people I worked with there. Then I finally, after a few years, I came back to work for Amazon, or for Microsoft in the Azure division, working on archival storage. Archival storage is a mechanism which allows you to store lots and lots of data that you expect you will probably never need to use again. It has the characteristic that it's extremely low cost and extremely reliable, because the last thing a customer will put up with is you stored this data on a backup tape and now you can't retrieve it. We had to guard against ever having that happen. So we had redundancy and all kinds of strategies to make sure that no matter what, we could always get your data back. Although our hope was you rarely would ever ask for it back. But if you did, we were guaranteed that we would get it for you. And the final thing I want to talk about is something called time travel debugging. This is a research project which turned into a major tool within Microsoft. The basic idea of it is we have a recorder which we can use to run a program, and when it runs that program, it's interactive. The program runs just as it normally would, but we record every instruction that's executed by that program. And by that, I mean every x86 or x64 instruction. And once we've recorded those instructions, we can play them back in the debugger. And we can play them back going forward or backwards. And we support all the breakpoints, including the data breakpoints. And there have been a whole bunch of cases where Microsoft, but to their embarrassment, actually had a bug that they couldn't reproduce while they were in testing, and they actually shipped code with the bug. And we had a few customers who discovered these nasty problems. And we sent them the code for recording a trace of the instructions executed, and they did that. And they sent it back to us, and we could load it in the debugger. And commonly, you have a problem like an access violation where you've tried to follow a pointer that's no good. So usually in those cases, you drop into the debugger, fire up the replay, and it goes up to the point where it crashes. And you look around in the state of the machine and you say, oh, we got a really bad value and we got it from this location in memory. So we set a data breakpoint on that location and then tell the debugger to execute backwards to find the code that stored that data in that location. And usually, by looking at the code around there, it's pretty quick to find out, okay, just what did you do wrong? Why did we get this really bogus address in this location? And it's solved a lot of problems within the product support group at Microsoft. In fact, they were one of our biggest fans. The other thing that was really excellent about time travel debugging was what we called Heisenbugs. These were sort of named after Werner Heisenberg, who invented the uncertainty principle. Heisenbugs were those bugs which are very hard to reproduce. And when they do reproduce, they never happen in the very same place. So you never know what to look for. However, if you ever are tracing when one of those Heisenbugs happened, you've got it. Once we've got a recording of it, we can replay that recording anytime we want, as much as we want, and they always replay in the very same way. And we can use all the techniques we have for debugging to track down and figure out what's going on. We can use data breakpoints, we can use breakpoints in the code. It's just really a much more pleasant environment. Now, I don't have a demo. I thought about doing it, but I figured it would take too much time. And one of the problems with demos is you're always at risk of having it blow up in your face. So the good thing about time travel debugging is you can try it yourself. Microsoft has made it freely available in a WinDBG preview. And if you want to know how it is we made this work, there is a paper that Sanjay Bansali wrote and submitted to the Usenix group, and it was actually published in 2006. Finally, there's a note from Visual Studio that this is fully integrated with Visual Studio Enterprise Edition 2019. And the final thing I put here is just the title for the paper, which Sanjay wrote, showing the co-authors and the people who worked with me on getting time travel tracing working. And so that's what I have to say.
Thank you very much indeed, Ron.
I don't know if there's any time for questions, but
Ron, we are out of time.
That's what I had to show.